All right, welcome. So in the last video or last couple videos, we've been talking about context-free grammars, and those are a model of computation that we use to define the context-free languages, and that's going to be the topic of this video. So I haven't formally yet defined the class of context-free languages, so a language is going to be called context-free if there's a context-free grammar for it, which I guess is probably pretty predictable given the name of the languages defined in terms of this model of computation. So we might ask ourselves, we've now defined two classes of languages, the regular languages and the context-free languages, and we might ask, what is the relationship between these two classes? We've actually already shown that one of the languages exists that is context-free, but is not regular. And specifically, that's this language here, L, 0 to the n, 1 to the n. We showed in a previous video that this was not regular using the pumping lemma. And then we also showed in a previous video that it was context-free by giving a context-free grammar for it. So we have one example of a language that is outside regular but inside context-free, meaning that we know that these two sets are not the same. However, we still aren't sure if one of these sets is contained within the other, as is depicted in this case, that the regular languages is a subset of the context-free languages, even though we have some maybe empirical evidence for that. In our last exercise video, we made some context-free grammars for some regular languages, and we found it wasn't necessarily tricky to make context-free grammars once we had a regular expression for them. And practicing that a bit maybe convinces us that there's sort of a automatic way that we might be able to do this, that there might be a way that given any regular expression we might be able to come up with a context-free grammar for it. And indeed, that's what I'm going to try and prove here. So I've got this stated here as a theorem. If a language is regular, then it is a context-free language. Another way of saying that is if you can make a regular expression for it, then you can make a context-free grammar for it. And indeed, that's what we're going to do in the proof. We're going to start, okay, so we're going to assume that L is regular, and we're going to assume that it has some regular expression based on one of our definitions of the regular languages, is that any regular language has a regular expression. So now what we're going to do, again, I'm going to call it R. I'm going to keep it general because I want that regular expression. I want this to apply to any regular expression, not just some, candidate that I pick. So now what I'm going to do is I'm going to use the definition of what a regular expression is to show how we can make a grammar for that same regular expression. I'm going to remind us that regular expressions were defined recursively, which is kind of convenient because our context-free grammars are also recursive. So let's start with some of the definitions of the regular expression that we remember. So our regular expression said, okay, R could be one of these terminating cases. Either a regular expression is just the empty set altogether, or it's the empty string, or a regular expression is some sigma from the alphabet, some symbol from our alphabet. Okay, and then the steps 4, 5, and 6 are all recursive versions of this, saying, well, you can union two regular expressions together, or you can concat two regular expressions together, or you can use the star operator to create a new regular expression. So the goal of our proof is to go to each one of these definitions of a regular expression and show that we can translate that or convert that into a grammar that has the same language. So let's start with our easy one. So if we want our grammar to generate nothing, which is a weird thing, it's just like a regular expression that generates nothing is a weird thing. We have a special rule that is this rule, that is S generates the empty set. So S generates nothing. Another way, interesting way that we sometimes depict this is we make a rule that just says S generates S, and that's the only rule in the grammar. So what that means is there's no way to terminate any recursive definition, so there are no strings that would ever be generated by that language. So there are different ways we depict this. Sometimes we use this special rule that I've got here. Sometimes we'll use this more conventional S generates S grammar to be the empty language. Okay, so let's continue then. What about the empty string? Well, of course, we can, if the language of our regular expression is just the empty string, it's easy to make a grammar for that. So our grammar just produces, as the start symbol just produces epsilon. Same thing with any symbol in sigma. We can just replace the epsilon with sigma. So we're going to take these as our simple terminating ones. And then we can see, okay, well, what about the recursive cases when we have a union? We saw this in our previous video when we were building some grammars. I said, hey, a union is like an or, and that's what the bar is in our grammars. Okay, so if our regular expression says, R is equal to R union, R1 union, R2, we can go get some new grammars for R1 and R2. Let's call them S1 and S2. Okay, and then we're going to make this new start rule that says, oh, which regular expression were you trying to be? Were you trying to be R1 or R2? If you're trying to be R1, go to S1. If you're trying to be R2, go to S2. And then recursively, we will define those S1 and S2 using, hopefully, the same construction that we're building right now. Assuming the construction is completed, it will work. So let's keep going, hopefully that we can complete it. So union worked. Let's consider concatenation. Now when we're trying to concatenate these together, again, concatenation is sort of a natural operation in strings. We don't even usually write the little dot between them. We usually just put them together. And certainly that's the way it would work in our grammars. Basically, we're saying here, concatenation is built into regular expressions. Concatenation is also built into grammars. We use different symbols for them, but we're just going to do it the exact same way. In effect, we did the same thing for union above. Again, different symbols. We used a union for regular expressions. We used a bar for our context-free grammars. So the only one that maybe gets a little bit curious is when we want to do star. And we looked at this in some of our examples in our previous exercise video as well, that when I want to do a star operator, I usually rely on this duplication in my grammar, which is an S goes to SS, so that it can duplicate itself as many times as it wants. That's like the star operator, right? And then when it's done duplicating itself, it'll be a giant long string of S's. It has to terminate itself with S1s, where the S1 is whatever we're trying to star, R1 in this case, okay? You'll notice that we put the epsilon on there as well to allow for the case where we are going to do 0 copies of this as well. Okay, remember that's epsilon is always in the language of the star operator, and that's just, we're making sure that that's in there as well. So this is a very straightforward kind of process. It's a process that we actually put into play in our previous exercise video for some of them. We didn't do it this formally, but we were like, oh, I've got a union, let's make it a bar, or oh, we're going to concatenate, let's do that, right? So we put that together. We've already kind of used this, and now we've seen it formalized to show that indeed the set of regular languages is a subset of the context-free languages. And that was the point of this video. So this was a short video. Thanks a lot for watching, and we'll see you in that next video.